Hi, my name is Alexander Savich, and in this presentation I will talk about Lambdas, one of the Java 8 features that you can now use with Coherence as well. So let's get started. In the first part of the presentation we'll cover what Lambdas are and why they're important to Java developers. I'm assuming most people already know this stuff, so we'll keep it short and only talk about the important bits and things that are relevant for Coherence Lambda support in particular, such as Lambda serialization, for example. In the second part, I'll show you how you can use Lambdas in Coherence to write cleaner, easier to read code, and improve productivity. There are a number of Coherence features where Lambdas can be used to your advantage. For example, you can use Lambdas as value extractors. You can use method references to make your code more type-safe and easier to refactor. Map listeners, where you can use Lambdas to provide the handlers for the various events Coherence dispatches. We'll briefly discuss how Lambdas are used in the Stream API, which you can find a lot more about by watching Java 8 Features Stream API presentation in this same YouTube video series. And then we'll talk about entry processors, which can now be implemented as pure closures, completely eliminating the need for custom serialization, custom classes, POF type registration, etc. More importantly, because of the way we implemented Lambda remoting, which we'll cover in more detail in the third part of the presentation, they allow you to introduce new logic into running cluster without the need for a cluster restart, which is something you really couldn't do at all before Coherence 12.2.1. Finally, we'll touch upon default map methods introduced in Java 8, which are now also safe to use in Coherence. We will also discuss one area of the Coherence API where you technically could use Lambdas, but you really shouldn't, as it would have detrimental effect on your application's performance. But more on that in a minute. In the third and final part of the presentation, I will talk about some of the challenges in the standard Lambda implementation that we had to overcome, what we did to accomplish that, what are the limitations of the approach we took, and how you can work around those limitations. You'll also see how all of it works in practice, as I'll do a demo that shows how new entry processor can be introduced into a running cluster without the need for a restart, and how multiple versions of the same Lambda can happily coexist in a single cluster. So without any further ado, let's get started by discussing what Lambdas are and why they're important to you not only in the context of Coherence, but when writing Java applications in general. As I'm sure you're already aware, Lambdas are probably the single biggest, and I'd go as far as to say a defining feature of Java 8. We've been waiting for them for years, as they kept getting delayed from one Java release to another. But my personal take is that it was worth the wait. Java team did a really great job, and the end result is much better than what it would have been if they were included into the language prematurely. At the high level, what Lambdas bring to the table is the ability to use some of the really nice features of functional programming in Java without throwing away all the good object-oriented stuff that we are familiar with. Effectively, they enable a hybrid object-oriented functional programming style by allowing it to both pass Lambdas around as method arguments and return them as the results. It is a style that I personally like a lot, as it allows me to choose the best approach for a given task. That said, it is one thing to add functional aspects to the language itself, and another to actually take advantage of those aspects in the existing class libraries. Java team did a great job there by adding support for Lambdas in several places. They added them to the existing collections library, where they introduced functional style methods such as for each, as shown in the example on this slide. They also introduced a completely new Stream API, which is very much functional to its core and provides a very nice, concise, and readable way to query and aggregate streams of things. They provided a set of frequently needed functional interfaces, such as function, predicate, consumer, and supplier as part of base class library. And last but not least, they allowed any interface with a single abstract method to be treated as a functional interface and represented by Lambda. This last point is critical, as it means that we can use Lambdas to represent existing interfaces such as runnable, callable, and comparator, as well as any interface from any third-party library that has a single abstract method. This includes Coherence as well. Another important aspect is that Lambdas can capture effectively final variables from the surrounding context, as you can see in this example. This means that Java lambdas are closures. They can carry not only the behavior, but they can carry the state with that behavior as well. You can see in this example, the lambda passed to the for each method captures the father variable declared in the surrounding context and prints it out. This slide should be fairly self-explanatory. Unlike anonymous inner classes, which require quite a bit of ceremony, lambdas allow you to specify only what's absolutely necessary, the code to execute. Everything else, such as which functional interface the lambda represents, in this case runnable, as well as arguments and return types, are inferred from the call site. It makes, as you can see from the examples, it makes the code much cleaner, much more to the point. Lambdas in Java do support serialization, but unfortunately not by default. You can make them serializable, as this example shows. Even though runnable itself is not serializable, we can make it so by casting it to an intersection of both runnable and serializable. Another option would be to implement an interface that extends both runnable and serializable, such as serializable runnable, and then declare a variable R to be of that new type. This is important because of the way Java implements lambda serialization. Unless the lambda is serializable, the metadata necessary for serialization, which is shown in the bottom example, is not going to be present on the lambda at all. So even though we don't use standard Java serialization to marshal lambdas across coherence processes, as I'll talk about later in the presentation, it is still important that every capture lambda is serializable, as we still need the metadata in order to implement our own serialization mechanism. So, in order to support lambdas, Java team introduced many new functional interfaces in Java 8. They introduced things such as function, predicate, supplier, consumer, and then some things that really probably shouldn't be there, but they're necessary, such as by consumer, which takes 2 arguments, unlike consumer, which takes 1, etc., etc. There are also primitive variants of many of these interfaces. And we also have some of interfaces that we are familiar with already, such as runnable, callable, and comparator. They are also functional interfaces. They have a single abstract method. Unfortunately, none of these interfaces are serializable by default, which effectively makes them unusable in a distributed environment and is one of the challenges that we had to overcome to make them usable with coherence. So let's talk about lambdas in coherence. We have a few existing functional interfaces as well, things like filter, value extractor, map event transformer. All of those things have a single abstract method, so you can use lambdas to represent them. We've also made entry processor interface a functional interface by basically implementing it. Entry processor used to have 2 abstract methods, process and process all. We've implemented process all as a default method, which effectively turned the entry processor into a functional interface. So now we can actually use lambdas to represent entry processors. The good news is that all coherence functional interfaces are serializable as well, which means that they are usable in a distributed environment, and we will get lambda metadata when we use one of our own interfaces. But what about standard Java interfaces? We still depend on those things. We still depend on Java functional interfaces, for example, in the Stream API. We depend on them in the default map methods that were introduced in Java 8. So we need a way to make those serializable as well. And same thing with things like runnable, callable, and comparator in particular. I mean, those things might be used in a cluster, so we need a way to make them serializable and so we can marshal them over the wire. So what we did is we made them all serializable as well. Basically, for each functional interface in Java util function package, there is an interface with the same name in the remote class that extends it and makes it serializable as well, as you can see in the examples on the slide. As you can see, function remote.function extends Java util function and extends serializable. Same thing with runnable. Once we extend both interfaces, our remote.function interface becomes serializable, and any lambda captured as such will be serializable as well. However, we didn't stop there. Many of the standard function interfaces have default methods that are typically used for composition. For example, predicate has and, or, and negate methods that return another predicate. We have overridden these methods to ensure that they both capture and return serializable lambdas as well, so you can safely use them with any of the remote functional interfaces that we defined. We've also added a static capture methods for each functional type. These methods can be used to ensure that the lambda is captured as a remote serializable lambda, but this is really not their main purpose, and as you'll see shortly, you should rarely have the need to use them that way anyway. However, they can be very useful when you need to compose lambdas, as you see in the examples. For example, the function interface has an and-then method, which allows you to chain functions by applying second function to the result of the first. Unfortunately, you can't call composition methods on the lambda directly, as the first example attempts to do. It simply won't compile. You need to help the compiler by providing additional information, which you can do either by casting, or by using intermediate variables, or by using capture method that does nothing more than return a lambda it captured as an argument. The downside of the first two approaches is that you end up with a lot of parentheses, angle brackets, and type names that make the code much longer and much harder to read than it really should be. If you're anything like me, you'll agree that the capture method example at the very bottom is both shorter and reads much better than the other two approaches. And you can make it even shorter if you want to do a static import. As I mentioned a moment ago, you really should rarely have to worry about any of this, as we've overloaded all relevant methods in the Coherence API to capture lambdas as remote serializable lambdas automatically. As you can see in the first example, for any method that accepts standard Java functional interface as an argument, we've added an overload of that method that accepts remote version of the same interface. And our overloaded method will always be preferred by the compiler. The reason for this is that the Java compiler always binds the call to the most specific method it can find. Because remote function extends function as well as serializable, it is considered more specific by the compiler, and it will always be called with a captured lambda, which will automatically become serializable. Even though this is a compiler feature that most people will probably never have to think about, it works wonderfully in practice and ensures that the end users of the API don't have to jump through hoops in order to make Lambda serializable, even though it does put some additional burdens on us as API implementers to create and maintain necessary method overloads. This concludes our discussion of Lambda serialization and shows that for the most part you really shouldn't have to think about it when using standard Coherence API. However, if you're implementing your own API that accepts lambdas as arguments and calls coherence under the hood, you do need to think about it. But even then, as long as you use remote functional interfaces that we provide instead of standard non-serializable ones that come with JDK, you should be okay. And if you define your own functional interfaces, simply make sure that they're serializable from the get-go. Now let's move on to more interesting topics and look at where and how you can use lambdas when writing coherence applications. Before we do that, however, let's get out of the way one thing that you really shouldn't use lambdas with, even though technically you could, which is coherence filters. Simply don't do it. While filter itself is a functional interface, index-aware filter is not. An index-aware filter is what you need to make coherence queries perform well. If you use lambda as a filter, indexes will basically not be used at all. It will likely cause deserialization of all the data, it will lead to heavy garbage collection and possibly even out-of-memory errors. Instead, what you should do is use our standard filter API. And as you'll see in a moment, we also have a new filter domain-specific language, filter DSL, which provides a much simpler and safer way to create filters using lambda-based value extractors. So now that we've covered that, let's really move on and talk about things where you should use lambdas, starting with value extractors. One way to define a lambda is basically by using a method reference, which is represented by a class name followed by colon, colon, and then name of the method. There are also other options you can use. You can refer to static method. You can also refer to instance method on a given instance. But this is by far the one that is going to be most useful to you as coherence developers when you need to define value extractors, because it is by far the easiest and the best way to define them for several reasons. One, it is type safe. We know, and more importantly, the compiler knows both what you're extracting from and what the result of extraction is. And our new filter DSL and filter classes can take advantage of that to ensure that you specify correct arguments. In the example above, if I specified something other than an integer as an argument to the less method, the compiler would complain, as it knows that person_getAge method returns an integer. Two, these things can now be easily refactored by your IDE. If you change property name in the person class, all references to it will change as well. This is much better than a magic string or a constant-based approach, which we had to use with reflection extractor for years. Although I should mention that for compatibility reasons, we do support mixed use of method references and the reflection extractor. This means that you could have an existing application that creates indexes using reflection extractor, and another possibly new one that queries the cache using method references as extractor. As long as both are using Coherence 12.2.1, you cannot have one version running on older Coherence version and then client application running on new. For example, you have to use Coherence 12.2.1 in both on the server and on the client. But as long as they're both using Coherence 12.2.1 and the method names match, everything will just work and the indexes will be used. While we're on the subject of value extractors, let's look at how we applied functional programming to Coherence API most often associated with them, which is a filter API. First of all, the generic support that we've added throughout the API, and about which you can find out a lot more in Brian's presentation, allowed us to make the value extractor itself strongly typed. We now know both what we are extracting from and what the type of the extracted value is. This allowed us to make all of our filter implementations safer, as they don't blindly take an object as an argument anymore, but something that is type compatible with the value returned by the extractor they use, as you can see in the first example. Less filter now has T, which is the type it is extracting from, and E, which extends comparable of super E. And then you can see the constructor for less filter basically takes the extractor of super T and extends E, and takes value of type E as a second argument. So we can basically match what the extractor is returning with what we are providing as an argument to the filter. Of course, this is not sufficient on its own. We still need a value extractor implementation that allows compiler to infer the extracted type. The legacy reflection extractor unfortunately doesn't. It has been generified. You could provide the correct types yourself, which will allow compiler to do what it needs, but that's a bit cumbersome. However, method references automatically provide all necessary information to the compiler and will automatically make your filter API usage safer. However, we didn't stop there. We've also added default implementations of several functional methods to the filter interface itself. Some of them are the usual suspects found on the Java predicate interface, such as AND and OR. The difference from the predicate is that they will create fully index-aware coherence filter instead. We've also added some useful methods that are coherence specific, such as associated with, for keys, for partitions, and as limit filter, which make the creation of key associated filter, in key set filter, partition filter, and limit filter simpler and more readable, as you can see in the second example. Here we basically create a like filter, then we use AND method that we added to the filter interface. We end it with a less filter, which basically creates an AND filter instance. And then on the AND filter instance that's returned, we call associated with method passing the key, which effectively creates a key associated filter for the whole thing. Finally, we've also added filters helper class, which basically provides a number of static factory methods for all built-in filters and one static import later, we end up with the example at the very bottom, which has no new operators, no angle brackets, and yet it creates an end filter wrapped with a key associated filter containing 4 filter instances altogether. Just to remind you, this is equivalent to this pre-12 to 1 code. That's a lot less typing and much better readability, if you ask me, not to mention the added benefit of type safety and the ease of refactoring. So I think you'll agree if I say that we made filter API a bit friendlier to use in 12 to 1. All right, let's move on to the next topic and talk about how Lambdas allowed us to make map listener API a bit nicer as well. Well, the map listener itself is not the functional interface. We've created a simple implementation of it that allows you to specify Lambda-based event handlers for each type individually, or a singular handler for all events, as the top example shows. It really depends on what you're trying to do. The example doesn't show this, but you could also register multiple handlers for the same event type, and they will all be called when the event is received. This basically eliminates the need to extend the abstract map listener and override the method you care about, or to extend multiplexing map listener when you want to handle all of the events the same way. Simple map listener effectively replaces both of these base classes and allows you to do exactly what you want to do, whether it's handling a single event type or specifying multiple handlers for each of the event types. The next topic we're going to cover is the Stream API, which is another new feature of Java 8 that depends on Lambdas. It is the first significant API, and the first new API in the base class library that provides functional programming constructs. It is very much based on Lambdas. It uses Lambdas heavily throughout. And in that essence, it is a query and aggregation API for various stream sources. Typical stream sources are collections, files, sockets, you name it. Basically, everything that can produce some data can be used as a stream source. It allows you to define a pipeline of 0 or more intermediate operations and a single terminal operation, and then that pipeline gets evaluated when you actually call a terminal operation. It also allows you to replace external with internal iteration, which is the basis for enabling parallel execution of the stream processing. So you could have the same stream definition that does some processing sequentially, and you could basically flip a switch and say, okay, I want this to be done in parallel, and the API, the Java, will do it in parallel across multiple threads. So how does it work in Coherence? We basically implemented support for the Stream API with Coherence name cache as a stream source. Internally, it uses Coherence aggregators to parallelize execution not only across threads, but across all cluster members. So we can actually parallelize stream execution across multiple processes on many machines, while at the same time preserving the API and the semantics defined by Java. So the stream, for the most part, and I'll cover the differences in my stream presentation, for the most part, stream code that uses stream looks exactly the same, but it is completely different underlying mechanism that executes the stream. All right, so let's move on to by far. Again, if you're interested in streams, watch Stream API presentation in this YouTube video series. It has a lot more information both on how the streams are implemented and what the limitations and differences and some optimizations that you can do when you're using them with Coherence are. But now let's move on to the most interesting use case that Lambdas enable in Coherence, which is the ability to implement entry processors as Lambdas. If you think about it, entry processors were always functions that we wanted to apply to cache entries, but we had to implement them as classes because that was the only option Java provided. This also meant that we had to implement them as serializable classes because we were marshalling across process and network boundaries. And if POF was our chosen serialization format, which for most customers is, we had to implement serialization code, register them in POF config, etc. It worked, but it was a bit more cumbersome than it had to be. With Lambda support in 12 to 1, you can now write entry processors as functions that they really are, and you don't have to worry about serialization of captured arguments or the Lambda itself, as we handle all of that for you automatically, regardless of which serialization format you use. It is truly liberating. I mean, I've enjoyed working with entry processors with Lambdas ever since we added support, and I'm sure you'll find yourself writing entry processors much more frequently and in way less time, just like I did. I have to admit, and sometimes I would avoid writing a new entry processor just because I didn't feel like doing all the other things that had to be done in order to get it to work. Now there is absolutely no excuse for doing that. I mean, it is as simple as writing a Lambda. And you can see that in the example. Of course, the example on the previous slide is just a stateless Lambda. We're basically sending an entry processor in that simply extracts single attribute from an entry. More often than not, entry processor will carry some state with them, which means that they will really be represented by a closure that captures one or more arguments and not the stateless Lambda. A good way to implement such closures, for a number of reasons that I'll get to in a minute, is to return them from a static method. This ensures that all captured arguments are local variables, as you can see from this example. And this is quite important when we want to send such Lambda over the wire. It also improves the readability of our entry processor invocation, as you see at the bottom. So in this example, we have a split method, which is a static method. It takes factor, which is our split factor, as an argument, and that argument will actually be captured inside of a Lambda. So if you look at the Lambda itself, that we are simply returning from this static method, the Lambda itself is your typical implementation of an entry processor, basically of a process method of the entry processor. It takes entry as an argument, it gets the value from it, it changes the quantity based on a split factor, it changes the price, purchase price based on a split factor, and it updates the value, and then it returns the updated value. So we can invoke it by simply saying positions, invoke all, where position is Oracle, split it by 2. So it's very readable, it's very nice, and all it took is basically a single static method in order to capture the arguments. Of course, if you simply wanted to change the values, in the previous example, we actually wanted to return the values after the split. But if you simply wanted to change the values and you didn't need the results, you could use one of the new default methods that were introduced in Java 8, such as replace all. And in this case, the actual Lambda becomes a bit simpler. As you can see, instead of taking an entry, and returning entry processor, we are now returning by function that takes key and value as arguments. And so we don't need to do all the things we had to do with entries. We don't have to get value from an entry. It's already provided for us. We don't have to update the value of an entry. It will be done automatically based on the return value of this by function. So we can do the same thing by using this by function and calling replace method instead. So do replace all, position get symbol Oracle, split by 2. As I said, the limitation is that there are no return values. So replace all returns void, so there is nothing that you can get back. So it is simpler. It still uses entry processor under the hood. Might be the right solution for many scenarios. If you need return values, then you can always fall back and use full-blown entry processor instead. In addition to replace all, Java 8 added a number of default methods to map interface. Things such as compute, compute if absent, compute if present, for each, getter default, merge, put if absent, remove, replace, etc. All of these are pretty much self-explanatory, and they are all useful. They're all very nice methods. And in theory, these methods should all work with coherence as well. However, in practice, they were completely broken. Or actually, they broke coherence because they assume data locality, which we do not have, and they provide no concurrency guarantees, which we actually do need. So do not use them if you're running older version of coherence on Java 8. They will be there because they were added to the map interface, which coherence name cache extends. But if you use them, then you might run into trouble. Now, that said, we've re-implemented all of them in a performant, cluster-safe way, basically on top of coherence entry processors in 12.1, so you can safely use them in coherence 12.1. Alright, so now that I found a way to plug in one of my favorite quotes, we can wrap up this part of the presentation and pop the hood to see what's under it and how Lambda support in coherence differs from the built-in support in Java. And more importantly, what the advantages and limitations of the approach we've taken are and how you can work around the limitations. One thing that we fortunately realized very early on was that the standard Lambda serialization support in Java wasn't going to cut it for a number of reasons. For one, we needed to support multiple serialization formats, while Java supports only one of them. This means that we wouldn't be able to use Lambdas with any caches that use POF. We wouldn't be able to use POF types as captured arguments. That would effectively make Lambdas unusable for the vast majority of our customers. So that was showstopper number one. Second thing was that coherence customers frequently run multiple client applications with possibly different versions of the same class. Java provides no strong guarantees when it comes to stability of the names that it uses for the syntactic Lambda methods the compiler generates. This effectively means that you need to have the same version of every class that captures any Lambda anywhere, everywhere. That's basically showstopper number two. We cannot put that constraint on our customers. Finally, we saw Lambdas as an opportunity to do something that customers have been asking us to do for a while and something that we really wanted to do, which is to allow them to introduce new logic into running cluster without the need for a cluster restart. This wasn't exactly a showstopper, but it was a really big, nice-to-have goal on our list. And considering that we already had to solve the serialization problem because of the first two issues, we decided to tackle this problem as well. The final result is that we now have a framework in place that can take almost any Lambda, and I'll talk about limitations in a bit, capture not only its metadata, but its implementation as well, its bytecode, send it across the network and redefine and execute in one or more remote processes. So instead of talking about it in length and asking you to take my word for it, let's do a demo that will show how powerful and completely transparent for the coherence users this feature really is. As they say, picture is worth 1,000 words. So let's go to a demo. All right. So here we have a small client application that basically does nothing more than puts 5 entries in a cache if the cache is empty, and then runs an entry processor and prints out the results. So the entry processor is quite simple. We're doing people cache, invoke call, and on all the entries in the cache, we're going to invoke this processor. We'll get each person, we'll change the name to the uppercase value of the name, we'll print out that client version 1, change name to whatever the name was changed to, and then we'll return the modified, updated name. So, let's run this. In order to run it, we need to start some servers. And these are really just your standard default cache servers. They have no classes other than the person class in their class path. Everything else is just coherence jar and what comes with it. So I'll start a couple servers and then let's run the client. So I have 2 servers running. And let's run the client to get the data and execute. So the client will connect, and as you see, we get back uppercase names of each person. Now, if we look at the server logs, we can see in the server that client v1 changed name to Novak, changed name to Mario, everything is uppercase. The other server, the other 3 names were changed there. So it really depends where the data goes. I mean, it's partitioned, but each server responded to the entry processor that we sent. But now let's make this more interesting. So we still have the same client, we still have the same entry processor. Let's actually change client to version 2. And let's say we don't want uppercase names, we want lowercase names. And let's simply run the client again. So the client is recompiled, the classes are updated, and we see that we got response from the server with all the names in lowercase. And if we look at the server logs again, we can see that client version 2 changed name to lowercase version. and same thing on the other node. As you can see, I mean, all we had to do is basically change the implementation of the Lambda. The server now actually has both Lambdas. It has version 1 Lambda and it has version 2 Lambdas. And if you have different clients using different versions, they will both work depending on which client is making the invocation. Obviously, if you're trying to do the same thing but in a completely different way, might not make much sense, as in this example. But in general, you can actually evolve Lambdas over versions, and each client will use the appropriate version of the Lambda that it shipped with. And the server will basically manage all of them completely transparently. So as a user, all you're doing is writing a Lambda and sending it to the server to execute, and we do all the rest. So in order to accomplish this, which is obviously very powerful, we do have some limitations. We were able to gain some significant advantages, but nothing in life is free. There are limitations you need to be aware of. The first one is that the Lambdas must be self-contained. They should not reference fields or methods of the capturing class. They should not reference anything that isn't certain to exist, both on the client and on the server. They should only capture local variables. And a static factory method is a nice way to accomplish this. As you remember, I mean, I used it in the examples earlier. But what it basically gives you is, it is not a foolproof, but it will significantly increase chances that whatever you capture will be remotable, that we can take it and send it to the server. Because it will ensure two things. One, it will ensure that you cannot reference fields and instance methods of the capturing class, because you cannot get access to them from a static method. And two, it will give you an easy way to pass arguments that need to be captured, and it will turn those things into local variables. So anything that's passed as an argument to this split method, such as factor, could be possibly a field in the capturing class, but you have to pass it in as a argument to the method, which effectively turns it into a local variable. So that gives us 2 out of 3 things. So this leaves only one thing for you to worry about, which is to make sure that you're not referencing classes, static fields, and methods that do not exist both on the client and the server inside the Lambda. If you don't do it, this Lambda should be remotable, and we can redefine it on the server. The second limitation is that Lambdas cannot be nested. This can lead to some nasty surprises, including the one that I let slip through in the very first entry processor example earlier in the presentation, if you remember, which was basically people invoke call entry.extract person : get name. The issue here is that the person : get name is a Lambda, which is nested inside the entry processor Lambda. As such, we will never see it on the client, and we will not get a chance to instrument it and make sure that it implements equals and hash code properly, for example. When we create an entry processor instance on the server, it will create a standard Java Lambda for the specified method reference, which will functionally work, and that's probably the worst part. It will functionally work, but because it doesn't have equals and hash code, it will not be able to use any index that we might have for the person get name property, and we'll end up deserializing each entry it needs to process. The solution for this problem is simple. Instead of nesting value extractor inside the entry processor, you can assign it to a local variable and let entry processor Lambda capture it. That way we will process it, and we will add equals and hash code to it when we process captured arguments for the entry processor Lambda. And that way it will be usable, it will be able to find an index on the server. However, even though the solution is simple, the tricky part is realizing that you're nesting Lambdas in the first place. So, as always, make sure that you test your code and that indexes are being used as expected, with or without Lambdas, because that's typically how the problem is going to manifest. You will expect to use an index for something, and the index will not be used. So make sure that you do. Check for that. Which brings us to the end of this presentation. As I said earlier, Lambdas are a defining feature of Java 8. It is a feature that we've been waiting for a long time, and it's great to see that it's finally here. And for me personally, it's even better to see that I can use them in Coherence as well. Coherence allows you to use Lambdas as of 12.2.1 release as value extractors. Method reference is obviously the easiest way. You can use other Lambdas as value extractors as well, obviously, but method reference are probably going to be the most common one. You can use them as entry processors, which is very powerful, as you saw in the demo. You can use them as event handlers, a simple map listener class. which was added in 12.1. And there are also a couple of things that I couldn't put on a slide here, such as Stream API, which again, there is a separate presentation for that you can watch, and the default map methods. Coherence adds support for serialization of all standard functional interfaces that shipped with JDK using the remote class. And if you need to have those things serializable, you can simply use the interfaces that we already provide. And Coherence handles Lambda remoting in a dynamic way. By not depending on Java serialization, we were able to support multiple versions of the clients seamlessly, and we allow you to introduce new code into a running cluster. I hope you enjoyed this presentation and you're as excited as we are about the improvements we were able to make, both in terms of ease of use and the new features. If you have any questions or feedback, please comment on this video or reach out to us via one of the following social networking channels. Thank you.